Hi everybody, I'm going to talk about identifying equivalent protons and carbons in NMR in this video. So all this really boils down to is identifying symmetry within a molecule. So we've practiced that skill quite a bit in the stereochemistry section when we were looking at RNS and we were looking at chiral and enantiomers and diastereomers. All those are kind of using that, is there a mirror plane in this molecule skill, okay? So we're going to be using that skill for NMR. Because the key thing we want to keep in mind here is that the number of peaks in a proton or a carbon NMR equal the number of unique environments. Okay, so anything that is in an equivalent environment is going to show up under one peak. Okay, so if you have something that has a lot of symmetry, you might only have a few peaks, maybe like 3 peaks or so, but you have a whole lot more carbons and protons than that going on. But that's because anything that's going to be equivalent is going to show up as one peak itself. So what we need to be good at is identifying what those equivalent environments are. So first step, we're just going to start with this molecule here. So when we're looking at this one's pretty easy to spot. We have a mirror plane cutting right down the middle of that oxygen, okay? So the way that I like to do this with NMR is I'll first find as many mirror planes as I can. This one's a little bit weird because I have these guys going on, but we'll get to that in a second. But my main mirror plane in terms of the whole molecule is going to be cutting right through the oxygen. So all we need to do is look at one side of that molecule, okay? So whatever's on this side is going to be mirrored over here. So we really just need to look at what do we have going on in here. So we're looking for unique proton and unique carbon environments. So let's go ahead and just look at this a little bit. I'm going to draw out, how many H's do I want to draw out? I'll draw out the H's. I'll just try to do it small on the methyls over here. Okay, so that's all of my H's drawn out. So if I'm looking for unique proton environments, what I've got going on here is I've got these two. There is technically a mirror plane down kind of along cutting here in between those two H's. So these two are equivalent. So we're going to mark those as A. So those two are going to show up as one peak. And then these 3 sets of methyls, those are also going to be one environment. Okay, so that's going to be B. Okay, so basically whenever you have a methyl, you have free rotation there, so you're always going to be able to have a bunch of mirror planes kind of cutting down one H and then having the other 2 H's mirror it. And then CH2s, they're a little bit special. We might see when they might be a little bit different, but we're going to keep it fairly simple for now. So at this point, that's all of the protons that are in the box that I've drawn. Let's look at the carbons real quick. So for carbons, I've got this CH2 peak. Okay, I've got this carbon that's attached to 3 methyls, so those are 2 different things. And then again, we're looking at these 3 methyls. Those are all going to be the same. So it's basically like a methyl of methyls, right? Where we have all of those planes of symmetry around. So we're going to have 3, 3, 3. So when we're looking at this, when we're finding the equivalent ones, it's important to keep in mind that this carbon over here is the same as carbon number 1. This carbon is the same as carbon 2. And then these are all the same as carbon 3. Okay, so this molecule, all in all, is going to have 3 carbon peaks. Okay, and it's going to have 1, 2 proton peaks. Okay, and it's really, really important to keep in mind here that proton NMR only shows up hydrogens. Okay, all you're doing is you're looking at hydrogens and seeing what influence they have in terms of like chemical shift and stuff based on other atoms that they're close to, but the actual peaks are made up of the hydrogens. Okay, and in a carbon NMR, you're only looking at carbon atoms. Okay, you're gonna again see the like kind of influence of other things, but I don't ever want to see somebody assigning like an oxygen a peak in an NMR, because the oxygen is just an influence, but it's not showing up there. Okay, so that's going to be this one. We're going to have 3 carbon peaks, 2 proton peaks, and that's going to be our NMR for this one. Okay, and you can tell a lot just by the number of peaks, because you can get a lot of information from that and do some really quick kind of, you know, process of elimination type stuff so that you can kind of get rid of some ideas. Alrighty, so let's look at this one next. So this one, very similarly to our stereochemistry stuff, if it is not already drawn in a way, in a particular conformation that makes it easy to see a plane of symmetry, we have to do some bond rotations in order to get it to something that looks more symmetrical. So what we want to do here is we want to rotate this around this bond. So we're going to end up with something more like that. So I still have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Still have the same number. There's no like stereochemistry here that got changed. All I did was rotate it. So once we have it in this conformation, then we can see it quite a lot easier that yes, I do have a plane of symmetry right down the middle. So again, I can kind of make my little box. And then basically we're just counting the unique environments for proton and carbon within that box. So for proton, let's go ahead and do that with purple again. So we're going to have CH2 here, but keep in mind that's different than the CH2 over here, because this one is between 2 CH2s. That one's between a CH2 and a CH3, so those are all different. So this would be B, and that would be C. Okay, so our A, the 2 H's are the same, the B, the 2 H's are the same, and C, the 3 H's are the same. Okay, so then if we move on to carbons, in this case, our carbons are the exact same. So 1, 2, and 3. Okay, so in this case, they're going to match. So we're going to have 3 carbon-13 peaks and 3 proton peaks. Okay, so that's what we're looking for. It is important to keep in mind here that if you have a carbon that doesn't have H's on it, that's when your numbers are going to start differing, because then you'll have a carbon peak that you don't have protons for. But if you have protons on each carbon, you should have the same number. Okay, so let's move on to the next one. So this guy, if we're taking a good long look at it, we do not have any planes of symmetry here. So if I don't have any symmetry, that means that everything is going to be the exact same compared to itself. And I will say the one plane of symmetry that we have is like in the plane of the page where this H is wedged, that one's dashed, and then you're cutting in between them. So you do still have the CH2, the 2 H's are the same, these 2 H's are the same, those 2 H's are the same. Okay, but each carbon little section has its own environment. So in this one, we're going to have 1, 2, 3, 4 carbons. And then for protons, we're going to have 1, 2, 3. Okay, because again, this carbon of the ketone here, no protons on it, so we're not going to have any signal from that in the proton NMR. All right, so carbons, we're going to have 4 peaks. And proton, we're going to have 3 peaks. Okay, so the symmetry is going to be the first thing that I always look at, is like, how many peaks do I have? So let's look at some common examples on benzene. So this is one that comes up all of the time. Mostly because they make for really good kind of NMR analysis, and they're really good at kind of testing your symmetry eye. So in this case, we're going to look first at a situation where you've got two substituents on benzene and you've got two identical substituents. Okay, we'll do two different substituents next. Well, for now, we're going to stick to two identical substituents. So the thing that I want you to keep in mind here is I want us to remember the resonance hybrid of benzene. So it's really this fully delocalized circle. So when you're looking at symmetry for benzene, don't include the alkene bonds in that, okay? Actually, I'm gonna not say alkene, we're gonna say pi bonds. Okay, some students hesitate on, drawing a symmetry plane when the pi bonds are not completely symmetrical, but just keep in mind that they're a circle, so it's going to be symmetrical however you cut it, okay? All right, so first one, the one on the left, this is called an ortho substitution pattern. So when they are a 1, 2, that's ortho. So the next one is meta. That's a 1, 3. And then para is 1, 4. So I'm just going to have that down there because I'll inevitably end up saying ortho, para, meta, whatever. Okay, so first one, we'll do the ortho on the left. So I have my two X groups. I've got a nice cyclo, hexagon structure. It's not a cyclohexane, but nice flat structure here. That is my plane of symmetry. Actually, let me do it dotted. Okay, so I've got my plane of symmetry here. We'll check to see if there's any more. If I try to go this way, that's not going to do it. That way, that's not going to do it. So this is the only mirror plane that I have. So let's go ahead and make our little box. And so now we basically just count all the carbons and all the protons that are in that box. Okay, so for my carbon, we're going to see 1, 2, 3. And then for proton, A and B. Okay, so we're just counting everything that's in that box. So for proton, we've got 2 proton peaks, and for carbon, we've got 3. Okay, and this is going to be something that we're looking specifically in the aromatic region, which I'll talk about chemical shift in just a little bit. But that's kind of what we're focusing on. All right, let's move on to the meta. So for the meta substitution pattern, I've got a mirror plane right there. Okay, so I'm going to draw my box. And then we'll go ahead and add in our numbers. So the thing is here, when you are putting a mirror plane through atoms that are carbon or hydrogen, if they are on the mirror plane, you have to count them as well as a unique environment, right? Because this CH is different than this CH, because this one's close to the X's, this one's far away from the X's. So we have to make sure that we're counting those as different, because we don't have a plane of symmetry going this way, right? We don't have one there, but we do have one right here. So these are unique environments. So we want to make sure that we don't miss those. So our first carbon, we're going to count it over here. 2, 3, 4. And then our protons are going to be A, B, and C. Okay. And sorry, I should have been. I'll make sure that I fill in the ones up there too so that you can see it. Okay, so then I've got 1, 2, 3, and then B. Okay, so you should have like B is reflecting B, 2 is reflecting 2, and they should be in identical looking environments. Like this 2 is connected to X and 3, that's 2 connected to X and 3. So that's what we're looking for, is like complete exact, these are back the same thing. Okay, so for carbon peaks here, we're going to have 4. And then proton peaks, we're going to have 3. Okay, so you can already start to see how powerful this is, where you can tell just using symmetry and just counting the number of peaks you have, you can identify what kind of substitution you have on a benzene ring. Okay, and that's just by like counting. It's not by any like intense analysis or anything like that. Okay, so let's look at our para substitution. So for para, in this case, I have actually a couple of options here. So if there are multiple mirror planes, we need to make sure that we're getting all of them. So the first one that I see is just cutting straight in between those X's, okay? But then I also have one that's perpendicular to that right there, okay? So when I'm looking at this one, I'm actually just looking at a corner, right? Like a single pane of that window where I'm looking here, okay? So in this case, if I'm just looking at this one little section, my carbons, I'm going to have one carbon that's on the X, and then a second carbon, and that's going to be 2, 1, 2, 2, and then 1. Okay, so you can see from there that I have 4 carbons in total that make up that one environment. Okay, that's what I'm meaning here. So all of the 2s are going to be 1 peak only. All right, so we're looking at that. For carbons, we've got 2 carbon peaks. And then for proton, we've got A. And we only have the 1 proton that's in that box. So all of these are A. So we just have 1 proton peak here, okay? Alrighty, so let's look at an instance where we've got 2 different substituents. So now, if I'm looking at this, if I'm just kind of looking to see where I had my plane of symmetry before, I had a plane of symmetry right here. But now, the X and the Y do not reflect each other. So I don't have any mirror plane here. Okay, so in that case, I have to count every single environment as different because this carbon is closer to the X, this carbon is closer to the Y. Those are 2 different things, 2 different environments. So we're gonna have 1, 2, 3, 4, 5, 6 carbon peaks. And then for proton, we're gonna have 1, 2, 3, 4. All right, let's look at the meta. So again, my meta, I had it right down here so that my X and my X could reflect. Now I've got an X and a Y. Those no longer reflect each other, okay? So again, no mirror plane. Okay, so let's count this out again. So we're gonna have 1, 2, 3, 4, 5, 6. Another 6 carbon 13 peaks. And then A, B, C, D, 4 proton peaks. Okay, so this is the first time that we actually have 2 things that fall under the same category here, okay? But nicely enough, I'll talk about it in the other video. There are different ways that you could tell the difference between these 2 substitution patterns. All right, so then the last one are para. So if I'm looking here, I had 2 mirror planes for my para. I had one going here and one going here. Okay, so if I'm looking at this one, oops, that was not where I intended to do that. So right here, I don't have my X and my Y mirroring each other, right? They do not match up. So I certainly don't have this one anymore. That's gone. But I still have that mirror plane if I just cut the X and the Y in half. So let's go ahead and draw that in. So if I just cut right down those atoms, then I can again have like a 1/2 type of look. So I can have 1, 2, 3, 4. And again, we're looking at anything that's on that mirror plane as well as in that box. And then for protons, A and B. Okay, so we're gonna have 4 carbon peaks. And then 2 proton peaks. Okay, so we've got A, B, and we've got 2, 3. Okay, so that's kind of how we're going to be looking at equivalent protons and carbons to just see how many peaks we have going on. Alrighty, so let's look at chemical shift a little bit. So this is kind of the full reference table that you're going to have when we're starting to do this in class. I'm going to be printing these out for you. It is already posted on Moodle, so feel free to use it. This is the one for the IR. This is all that I care that you know about IR. This is the NMR reference table. Okay, so you can see we have carbon and proton chemical shifts. Make sure that you're noting here the scale. So if you're not sure whether you've got a carbon or a proton in your hands, scale is going to be the best thing for you. You're not going to be finding many carbons that don't go past 10. So just keep that in mind. The other thing is carbons are always going to be like a single straight peak. And then the proton, as you've seen already, you have a lot of like splitting of peaks. So you have the quartets and the doublets and all that. Okay, so a couple things that we got to talk about here just in terms of nomenclature. So aromatic, okay, remember that's going to be our benzene. So we're looking for benzene here. This, I really want you to be thinking electronegative atoms. Okay, so CONX, and that's like a carbon that is connected to one of those electronegative atoms. Okay, the more electronegative it is, the more it's going to be pushed downfield. And that brings me up to the names here. So going to the left, that's going to be downfield and deshielded. And then to the right, that's going to be upfield and shielded. Okay, if you're not sure what the shielded means, what I want you to picture, it's really stupid, but like picture a shield of electron density. Okay, so your shield is electron density. So if you have electron density that's getting ripped away from a proton, it is getting deshielded. Okay, so think about if I've got, well, let's since we're talking about carbons, let's talk about carbon. So if I have a carbon connected to an oxygen, this carbon is delta plus, so it's getting deshielded. Okay, that's what we're thinking about. So if I have a lot of electron density that's kind of getting taken away, that's going to push me to the left of the whole spectrum. If I have something that's kind of giving me electron density, we're going to be pushed more to the right. Okay, and that's going to be more shielded. So think about things that are delta plus. Those are going to typically be your more deshielded, more downfield type protons. So stuff that's next to oxygen, stuff that's on oxygen, any type of carbonyl, right? Because any of those carbonyl carbons, right? Those are incredibly deshielded because, again, our good friend resonance. Okay, this guy is super deshielded, right? If I look at like an ester though, So an ester, I do have that. Oh, this is going to be messy. It's okay. Okay, so I do have it de-shielded. But I have these lone pairs nearby that can give it some electron density. And now it's a little bit more shielded. Okay, so that's why we see like the acids, the amides, the esters, anything that has something with lone pairs right next to the carbonyl, those can give us that shielding effect. And then we push a little bit more to the right to the more shielded side. Okay, so that's why aldehydes and ketones are going to be your very, very furthest, right? Okay, so just in terms of names though, just so that we're clear, so the alkene, it's going to be the carbons in an alkene. The alkyne, remember that's going to be our triple bond. That's going to be your alkyne carbons. And then alkyl, that's just any of your sp3 carbons. Okay, so the carbon NMR, I would say you're mostly looking at roughly chemical shifts. So you're looking at something here, here, here is going to be your main like big ticket items. Anything that you have in the alkyl region, it's not unhelpful, but it's not as helpful. Just in terms of kind of what are some of the different things that we have going on. So those are our look here first. Okay, so I would look there first and then count up the peaks, and then we can get some information about symmetry. All right, so for our proton chemical shifts, again, before we go anywhere on this, I'm just going to talk a little bit about some of the names here. So the acetylenic, that's just the H on a triple bond. Okay, alkyl again is sp3 H on sp3C. Allylic, benzylic, and alpha to carbonyl, those are all drawn out so that you can see what they look like. So we're talking about the H that's on the carbon that's next to a carbonyl, or the H that's on the carbon next to a benzene ring, or next to a pi bond. Okay, so that's what we're looking at here. We've got our allylic right there, benzylic there, and alpha to carbonyl there. Okay, so I want you to notice here that this 1.5 to 2.5 is more upfield than the alpha to oxygen, nitrogen, or electronegative atom. Okay, so when I have an H that's on a carbon that's attached to an electronegative atom, that's going to be more downfield than if I have an H that's next to a carbonyl. Okay, the reason for that is that this carbon is very delta plus. That one is less. Okay, because this carbon is actively attached to the oxygen. This one is just adjacent, right? So we're going to have less of an effect on the shielding and deshielding compared to here and here. Okay, so then vinylic, that's going to be the H's on an alkene. Aromatic, that's any of the H's on a benzene ring. Carboxylic acids, remember those are going to be our OH. So we're looking at that H. As you can see, this one, because it is so acidic, right, it's very deshielded. You can think about deshielded and acidity a lot because this OH bond is fairly weak because so much of that electron density is getting pulled up towards that oxygen, right? So this H, being as acidic as it is very, very delta plus. Okay, and then our aldehydes. we have right there. Okay, so when we're looking at this, this is what is going to be the easiest for you to use, just in terms of kind of the ranges that you're looking for. When we're going through this, I want you just to make sure like there's only so much that you can fit in a box. So keep in mind here that yes, this box goes to like 4.5, but make sure you're keeping an eye on the actual numbers listed in the box and not where the box ends. Okay, that's going to be the most important thing because I can only make them so small. So we don't want to be itty bitty so you can't see anything. So make sure you're looking at the numbers in the box, and then where they're placed along the chart is kind of as close as it's possible to be. Okay, so for just a reminder, this is going to only show hydrogens. And this is going to only show carbons. Okay, and again, we're looking for those unique carbon and proton environments. All right, so down here, we've got a little bit on specific functional groups. So one thing that we're going to look out for, this trend is helpful. So you can see like a CH3 is going to be more upfield than a CH2. And the CH2 is more upfield than the CH. So as you kind of stack other carbons on, we're going to see that slowly creep down to the D-shielded, okay? Just because the carbons are slightly more electronegative than the hydrogen. So that's something that we want to keep in mind a little bit. So that's going to be a trend that we'll see a bunch. And then these are very, very helpful. Okay, so one thing that we want to keep in mind here, OHs, NHs are kind of weird, right? So because they are on the more acidic side, you can have a lot of intermingling with the solvent that you're taking your NMR in. So you'll actually see a lot of variation in where those peaks show up, even from the same sample taken on different days. Okay, so the OH peaks, the NH peaks, finding those kind of more transient protons is a little bit harder. So because of that, because there's a lot of kind of switching between hydrogen and the deuterium that's in your solvent, you don't usually see the NH or OH coupling with the neighboring protons, and we're going to talk about neighbors in the next video. And they're generally more broad. Oops, Brad. Okay, so instead of like a really sharp singlet, I'm not doing that up there. Woo. So they're not really going to be sharp like this. They'll be more broad. Okay, so if you have something that's like fairly broad and integrates to one, that's probably an alcohol peak. And you can check that from an IR, right? Like that's a really good way to do that. Coupling constants, we won't get too deep into that. I don't know if we'll even talk about coupling constants. So for now, just ignore that. But that's kind of what I want us to think about. I would say the very first thing that I look at is I count the peaks, so I get an idea of kind of symmetry involved, and then I look at the chemical shifts of those peaks, okay? Because if we just go up and look at some of our examples that we had earlier, so if I'm looking at this, my eye goes straight to that oxygen, carbon 1, and the protons on carbon 1, those are going to be my most downfield peak. Okay, I don't have any pi bonds or anything like that. So this is the most electronegative thing I have around, and these are the things that are closest to it. So this is going to be my most downfield carbon and my most downfield proton. So if we're looking at this, this is a C connected to an O, and these are H's that are alpha to O. So these H's would be around probably 4 ppm, and the carbon would be around 70 or so. Okay, and I have those memorized, but you don't need to. I would say focus on if we can manage to find that C connected to O, that's why I picked 70. And then this alpha to O is why I picked 4. And the reason I picked those numbers specifically is I have just seen a lot of NMRs, so I know that a carbon connected to an oxygen is usually like 60 or 70, and then an alpha to oxygen H is usually around 4. Okay, so that's how we're going to be using this whole process. Alrighty, so next video is going to be integration and multiplicity. Alrighty, if you have any questions, please let me know.